Okay, in this video we'll be dealing with the Cholesky decomposition, and the Cholesky decomposition is just writing the matrix A in terms of a lower triangular matrix R and its transpose. Okay, sometimes it's written as L transpose, but here R isn't generally a unitary lower triangular matrix, just a lower triangular matrix. So to avoid confusion with LU decomposition, you can just call it R, okay? Now, this decomposition, Cholesky decomposition, is only applicable on symmetric positive definite matrices, and positive definite means that all eigenvalues are positive, okay? If you get 1 as 0, then that's positive semi-definite, and you can do a Cholesky decomposition, and obviously if one of them is negative, then it's not positive definite. So um, let us try to obtain this Cholesky decomposition from the LD L transpose decomposition, which was only applicable on symmetric matrices. Okay, what we can basically do is write down L D the power of half multiplied by the power of half L transpose. And now if we look at this, we can call this R, and if we call this R, then this is gonna be R transpose. So to do the Cholesky decomposition, we can just do LD L transpose decomposition, and then take L multiplied by the square root of the diagonal matrix as R, and you can then multiply R by R transpose to get back A, and that's going to be your Cholesky decomposition. Now for how you're going to get the square root of D, you're just going to take the square root of each element on the diagonal of D. Okay, it's that simple. So let's do an example here. We've got A equals 2, 3, 3, 5. And to obtain a Cholesky decomposition, we need two things. We need L and we need D. So we know how to get L, and D is the diagonal elements of U. So we're just going to do an LU decomposition, and then we're going to figure out how to reach the Cholesky decomposition. Okay, I guess it's clear now anyway. So we've got 2, 3, 3, 5. Gonna multiply the first row by negative 3 over 2, and then add that second row. So we're gonna have 2, 3. Here is gonna be 0, and here's gonna be 0.5, and this is A in reduced echelon form, so we can call this U. Now L is gonna be 1, 1, 0. Let me put some parentheses here. So 1, 1, 0, and we take the negative of that here, so 1.5. Okay, so we've got 1, 0, 1.5, 1 as L, and all we need is R equals L D the power of half. So we got L. L is 1, 0, 1.5, 1. D is this element in the diagonal and this element in the diagonal. So we've got 2, 0, 0, 0.5. Root D is root 2, 0, 0, 1 over root 2. So this is going to be R. We can carry on this multiplication real quick. Let me just get some space here. So let me also move this like, oh, come on, like this. Okay, yeah, now it's much better. Yeah, we multiply both of these. So we got the first row by the first column. This gives us root 2. Then the first row, second column is going to be, so 1 multiplied by 0, and then 0 multiplied by 1 over root 2 is just 0. Then we got 1.5 multiplied by root 2 is 1.5 root 2, and then we've got 1.5 multiplied by 0 and 1 multiplied by 1 over root 2. So we got here 1 over root 2, and this is going to be R, and A is going to be equal to R transpose. So we've got root 2 0, 1.5 root 2, 1 over root 2, and then we take the transpose, so root 2, 0, 1.5 root 2, 1 over root 2. Okay, so this is going to be the Cholesky decomposition for this matrix A. And yeah, that's it. Now I'll just talk about what happens if the matrix is symmetric but is not positive definite. In this case, what could happen is you would get negative numbers in the diagonal of U, so your D will have negative numbers. So when you try to take a square root, you're gonna get complex numbers, and that is not gonna just work out. Okay, that's gonna be all I wanted to talk about in the video. So thank you so much for watching, and bye bye.